Bismillahirrahmanirrahim. Welcome to the new lecture on theory of automata. So today we are going to cover pushdown automata. Basically, this is an automata with the additive power of stack into it. As we know, there are different types of languages. In this figure, we can see that in the smallest bubble there are finite languages, then their superset is regular languages, and the superset of these two languages contextual languages, and then there are many other kind of languages that would be the superset of contextual languages. So from this bubble we can understand that all the regular languages are also contextual languages, and all the finite languages are also regular languages as well as the contextual languages. In the same way, if we look at the constructs, so every construct of contextual language can identify the regular language and the finite languages. From the last figure, it is quite clear that the set of contextual languages is much bigger than the set of regular languages. We have different machines to recognize regular languages, and all the languages that comes under regular languages are identified by FA, TJs, and regular expressions. All the contextual languages are also regular languages, and they can be recognized by FAs and TJs. So what about the rest of the contextual languages? Because the bubble of contextual languages, you can recall, is bigger than the bubble of regular languages. So that means there are few contextual languages that are also regular languages, but there are few languages that are contextual languages but are not the regular language also. We need to have some machine for those languages also. The sole requirement of a machine is not only the language recognition, but some other major purposes are also served by that machine. These machines provide great support in the analysis of language through their formal graphical representations. We can understand the word formations, and we can understand or visualize the working of the machine. They facilitate the discovery of important characteristics that are about that language. So like we can see the patterns through the working of that machine. FS gave a thorough insight into the regular languages. We can generate unions, intersection, complements, we can do pumping leva. All need extensive support for FS and TGs. In previous lectures, we have been discussing the class of machines that accept the regular language. Corresponding to a regular language, there is a machine in this class accepting that language. And corresponding to a machine of this class, there is a regular language accepted by this machine. Hope you can understand both of the concepts. It has also been discussed that there is a CFG corresponding to regular language, and CFG also defines some non-regular languages as well. So the CFG that recognizes a regular language is known as the regular grammar. We have studied in the previous lectures. Here a question arises whether there is a class of machines accepting the contextual languages. The obvious answer is yes. The new machines which are to be defined are more powerful and can be constructed with the help of FAs with a new format. The new format that we discussed in the last slide is more like a flowchart, not like a graph in which we have been representing DFA and FA like that one. The first thing that is introduced here is the input tape. This is the part of the FA where the input string is placed before it is run. The input tape is supposed to accommodate every possible string. So it is a infinite string. You can place your string from left to right, and as soon as the string ends, the rest of the input tape is filled with the delta, as we can see in the next slide. We can see that we have placed a string a b b a on the input tape. So it is so, and the rest of the input tape is filled with deltas. The character delta indicates a blank in the tape. The input string is read from the tape starting from the cell I. That means it is from left to right. It is assumed that when the first delta is read, the rest of the tape is supposed to be blank. PDAs are the new machines resulted by some enhancement in the concept of FAs to recognize context-free language, and that enhancement is actually the stack. What we are going to study is a new and different pictorial representation that is more like a flowchart, not a graph. Enhanced recognition features explicit results about the acceptance and the rejection. Let's first introduce the elements of the PDA. I will be discussing the basic four ones here, and the two newly introduced will be discussed after few slides. The input tape, that is infinite. It is sequential from left to right. Cells represented and by the numeral Roman numerals. Delta stands for the blank represented by the represented at the end of the string. So we have discussed all these things and have seen the figures of that one. The start, that was the initial state in the F phase, is represented by this oval shape, and written start in it is equivalent to the minus state of Tg connected by the delta to any other state. Start will never have any incoming arrow. Another state is accept state. Is this equivalent to the final state of F phase? Once it is entered, you cannot leave that state. Reject state is equivalent to the non-final dead state. So once you enter into this one, you cannot leave that state. The state of FAs, DFAs is represented here in this new format with a diamond shape. Though the shapes are different, but the concept is 100% same. So all the input alphabet should be on the outgoing edges, so it will be having the same thing. Here you have a DFA. You can see how easily you can convert that one into PDA. So initial state, so let's call this one the read, that was this equivalent to that state. Let me pick some pen. Okay, so this is equivalent to this one, and this read is equivalent to this one. So you have added a start state here, and then mark it with this one, like this one, and you are going on, and just like this one, you have added the accept state here. When you end up with reading of the characters at the delta, you will say this string is accepted or this string is rejected based upon the logic. So this self loop is represented here like this one, and this self loop is represented like this one. So this edge that is going from initial state to the final state, this edge is here, and this edge is here. So it is very easy. The normal FA, DFA can be easily converted into the PDs because they are the same thing, but the format is different. Few things need to be noted, that the delta edge is not the epsilon edge, and delta edges only appear with the read boxes, the diamond boxes. The edge from the start state need no label, because start reads no letters, so that was not labeled. The accept and reject states are called the halt states, and once you enter into these states you cannot leave those states. Let's look at another example. So this is a FA having three states. Input symbol set is A and B. We can generate PDA against this one. So there would be three read statements, one accept statement before this initial this one here, the start state, and then there would be a few accept and final states. And you can easily map these ones. So these are the same states. So this loop is here, so this loop is here, this edge is here, this edge is here, so this edge is here. So you can see the mapping is very much direct. So you can for DFAs you can use this format also. Pushdown stack, or simply call it stack, it is a storage space in which you can place your symbols after reading from the input tape or whatever the logic is, and you can use it after some time using the pop operation. You store it using the push operation and you get it back using the pop operation. Before the machine begins to process input strings, the stack is presumed to be empty. So whenever you start a machine, so it is supposed that the stack is empty at the end, delta character would be at the bottom of that one. When a letter is popped, each of the elements below moves one position up. The empty location of the stacks are filled with the delta, as in the case of input tape. The stack has infinite length, just like the input tape. It is also infinite. Only the top letter of the stack can be read as per the definition of the stack. If the fourth letter to be read, then 4 pop operations are needed. So this is a stack, so every definition of stack is applied here. Popping an empty stack gives you delta. If your stack is empty and you try to pop, then you will get delta out of that. Let me introduce the remaining two states that are related to the stack. One is pop and one is push. You can pop from the stack, and that would be having all possible scenarios. On the outgoing edges, you have to mention all possible transitions here. And push, you can push and mention what character you are going to push in the stack. Just like here it is pushing A, just like here it is pushing again A, or you can say B or hash or X or Y, whatever you like, you can push it. But after that, if you place some different characters, so then you will be reading those characters, not the input symbols. The edges out of pop are labeled the same way as in case of read, one of each character so far. The branching can occur at pop states only. The push states have only a single outgoing edge. Remember this one. Nevertheless, a push state may have multiple incoming edges. So remember this fact that push state cannot have multiple outgoing edges. Here in this figure you can see an PDA in its full form. You are having a read state, you have having pop state, you have a another read state, another pop state, accept state, reject state, multiple reject states, and then start states, and last but not least push also. So starting from here you goes to the read state, and reading, you don't know which character you will be reading from that one tape, so either it would be A or B or delta. So if you read A, you push it in A and then go back to the read again. If you read A, so you will be pushing all the characters if they are the read as soon as you get either a delta or you read a B. If you read a delta, you will check whether the stack is having some character or not. If it is not having some character, then you can accept that one, and if it is having some characters either A or B, so it would be rejected as per this PDA. But if you are you read after some A's, you read some B, you pop and check whether it is delta or it is B. If it is delta and or it is B, so you reject it. So there should be, it means that conceptually there should be A's only in the stack. And if it is having A, then you go for the read, and then if you get a B here, you go back to the pop again. And if you read A and then if you pop A, you check whether it is read B. So that means you are, for every A you are going to read a B. So reading B and extracting one element from the stack. So that means you are calculating that there should be equivalent number of A's and B's, but all A's coming before all B's. So this is how it is. So spend some time, give it few inputs. So use this placing some valid or invalid inputs, and then you can understand it how it is working. So it is very important, do at least 4 or 5 inputs, at least 2 or 3 right inputs, valid strings, and 2 and 3 invalid strings. Don't forget, please. Let's look at the small comparison between PDAs and FAs. Both machines though have the finite number of states, but PDAs have a limited FA have limited storage, only one state can be recognized, but the PDA has unlimited storage capacity. Besides, PDAs can also keep track of the number of times a particular character has been read or the number of times a particular state has been visited. This is the additional thing that the PDAs have in its capabilities. Formally defining the PDA, the few things are the same that we have seen in DFAs, but the stack related things are new here. We have the alphabet, we have the input tape, we have stack characters. So here in PDAs there are two types of symbol sets. Number one is sigma and number two is tau. Tau is the set of symbols that you can place on the stack. Both sigma and tau can be the same, but sometimes we need to change the stack symbol set from the input symbol set to recognize. A pushdown stack infinite in one direction, the stack is empty initially. One start state that has no that is only the out edges, no in edge. Halt states, that is accept and reject states. They are push state, as many as you like, but it will be having only one outgoing edge. So there are two uh, kinds of branching states, that is read and pop. So at read and pop you can make your decisions and change your directions. So this is a tuple definition of formal definition of PDA. So you have to remember this one, just like you remembered the learned by heart the definition of DFA and NFAs. Repeating once again that if you read from the stack and the stack is empty, then it will read a delta character, just like you read it on input tape. It may be observed that if the push down stack is added to an FA, then its language recognition capabilities are increased considerably. So these would be the languages that are outside the regular language bubble and inside the contextual language bubble. Look at this machine. It is the same we have discussed earlier. Is it the same or it is different? So you can see the two edges are going to the same reject state, so it is possible. So you can also move this edge on this reject again. So you can have multiple reject states, or you can have one reject state and bring all the edges to that one. Let's take an example, triple A triple B, and it is placed and run this one on the machine that we see and that we have seen on the last slide. So this is the string on the input tape. This is the current situation of the stack. Stack is empty and it is filled with the deltas. We started with the start and read a character from the input tape. We read it from the tape and it is vanished from the tape, and then we push it into the stack. So we read A. So in this way we can loop this one and can push all the three A's in this one. After that we will come to the read 1, and then there would be B, and we will move towards the pop 1, and then we pop one element from the stack. So that is pop is one element when B is removed, A is removed from the stack, and one B is removed from the tape also. And then we will go to the read and we'll read a B, go back to the pop, read an A. So against one B it is removing one A from the stack. So that's why if at the end the tape would be empty and the stack would be empty, then it means the number of A's were equivalent to the number of B's. So this shows that this is A raised power n, B raised power n language. So you can see all the three are read. So now there is, now we have as we have seen and discussed in the last slide, that there would be delta on the input tape and delta on the stack. So it means all the A's are finished and all of B's are finished. So that means that shows that the number of A's and number of B's were equivalent. So this language is A raised power n, B raised power n for all the n starting from 0 to onwards. This process of running the string triple A triple B is being expressed in a tabular form. You can see it for the ease or calculation. You can use that format. Continue reading this slide. This is the machine we've been working on. So in a tabular format we can see all the changes in row by row, just like this one. So this is a on this side you can see the machine. At least you can have a idea how the inputs are moved. So start, your stack is having delta and the tape is having all the characters ending at delta. At read 1 it is delta and tape, so A is basically removed, 1A is removed and it is having double A triple B, and it is pushed into the stack. The tape is unchanged. For the next read, the two characters have vanished from the tape and it has read A from the tape, and the leftover are A triple B. The stack is unchanged. You push A against the character A, and now stack is having two A's. Your tape is unchanged. Next is read, and you read another character from the tape. You push A, you pushed one character in the stack. Then you read first B, you popped, you are moving towards the pop here now, like this one. So now you have read one character from this one. So there is one B is vanished from this one and one A is vanished from stack. In the same way, you're reading the character, second B, you're popping and you get an removed, one A removed. So you are having one A on the stack and one B on the tape. Reading, you read the last character of B, you popped the last character from the stack, and now your input tape, so the stack and the input tape is finished, both having deltas. You read, you get delta, and you pop, you get delta, and you accept if the delta is there. So this is how it is working. Remember that input alphabet set and the stack alphabet set can be same, it can be different, or they have some common elements, but they are actually the independent of each other. You can see that all the arrows that were going to the reject states are on the one reject state. There is no change, this is the same machine. Hey guys, do you remember this machine? This is a DFA for even language. I can understand that this is a very much familiar machine for you guys. If we convert it into PDA, it is very easy. We will apply 4 read state, one for this one for this, one for this, one for this, and carefully mark these edges, and 2 new states will be there. One is start, and there will be few accept states and few reject states. But this is because our regular language, so you don't need a stack for that one. This is the equivalent PDA. I think you can do it very easily. So there is a 4 read states, one start state, one accept state, few reject states. By now what we have studied is the PDA, that is the deterministic pushdown automata, and that was equivalent to DFA, deterministic finite automata. And you have seen or witnessed the equivalence of the two PDA and equivalence of PDA and DFA for the regular languages. And we have also seen another example for of PDA for context-free language, in which pushdown stack was used. Now we are going to start the non-deterministic pushdown automata, in which there will be no non-determinism on the edges. So that means we will be having multiple edges with the same labels. So the same definition of non-determinism that we witness in the NFAs. Like TGs and NFAs, if In a PDA, there are more than one outgoing edges at read or pop state. With one label, then it creates a non-determinism, and the PDA is called non-deterministic PDA. In non-deterministic PDA, no edge is labeled by a string of terminals or non-terminals, like that can be observed in TGs. Also, if there is no edge for any letter to be read from the tape, the machine crashes and the string is rejected. Just like NF is, in non-deterministic PDAs, a string may trace more than one paths. If there exists at least one path traced by the string leading to the accept state, that string is accepted. And this phenomena was the same in NFS also. Let's take this one as a example of NPDA where you can see there are multiple transitions for with the label A, uh, going from read 1 to push A and going from read 1 to pop 1. So that is actually the non-determinism. As discussed in the previous slide, here we can see that the non-determinism is at read 1 state. One transition is leading to push A and the second transition with the same label was leading to pop 1. This NPDA is basically of even palindrome, the W and reverse of W, like double A. The first part is A and the reverse of that one is A. And you can see more clearly in ABBA, where AB is W and the reverse of that BA is there. So it can be very easily recognized. So the new definition of, the updated definition of non-deterministic PDA would be as follows. Please go through in this definition, these points. These are the same as PDA. The sigma is there, tau is there, one start, accept, reject, push state, pop state. The change is here, you can see. May contains more than one outgoing edges with the same label. So that is the change. That was not possible in deterministic PDA. And the second change you can see here, that in the read state, it is saying may contains more than one out edges with the same label. So that is the only difference between the two. Let's take an example of context-free grammar, that is S goes to S plus S or S static S or 4. And we are going to draw its PDA, corresponding PDA. We can draw it like the simple method of generating NPDA from the context-free grammar is you go for the start, then you push an S, then go for the pop, and this is one transition S plus S, you can see in the last slide, and then the other one is S static S, but these are the in the reverse orders. Then there is a symbol S, you can get it from the stack. If you get an S, you read, and if it is 4, you come back to the pop. It is plus, you read a plus, and then you go back to the pop. If it is static, you read, and if it is static from the input tape, you go back and go for the pop. And then if there is delta, you read, and if the input tape is also empty, that is delta here, then you accept that one. This is the working of this string on this machine. Starting your stack is delta and your tape is filled with 4 plus 4 is static 4. You are pushing one S into the stack. Your tape is same. You're popping the stack. Now there is only delta and you have popped S from the delta. You are pushing S. If you have read S, you are pushing S. Then you push plus. So you are here on this. Let me highlight this one. Now you are actually here pushing S, then pushing plus, then pushing S plus S. You pop and you get an S. Against S, you read 4 from here. You read S, go and read 4. You read 4 there, and then you get plus from the stack, and then you keep on doing reading, and then pushing back things. And finally, you get the last element on the stack, that is S, and one element at the tape. You read, you pop that element, and then again you read that element. Now your stack is empty and your tape is empty. You check it with a pop and you check it with a read. If both are delta, you accept that one with this accept state. You are reading those two deltas. Number one thing, you should note that the letters are deleted from the tape instead of underlined. So this is just to show you. Otherwise, that letters from the tape are vanished or vanishes. It may also be noted that the choice of path at pop state can be determined by the leftmost derivation of the string belonging to context-free language. So remember these 2 points. Here are a few practice questions. The first 2 languages are, you can see that these are the regular languages. You can easily first draw FAs and then convert those FAs into PDAs. It would be very easy. And the second, third and fourth languages are context-free languages. When you see A's, you push all A's into the stack, and then you start getting B's. As soon as you start getting B's, you get remove one A from the stack and remove one B from the tape by reading that tape, and finally your stack would be empty. As soon as your stack gets empty, you start pushing B's into the stack and getting them back when you start getting the C's. In the next one, you can see that this is AM. This is the same logic that I have discussed right now. So I think this should be not N but M for monkey. So please correct it. In the first problem or the definition, you push all A's, and at the every third B you remove one A from the stack, and then you push all C's, and every second D you remove one C from the stack. Then the language of palindrome, language of non-palindrome. So these are all for you guys to practice. Thank you very much, guys. Have fun, and don't forget to do things that have shown you in the last 2 slides. Do them practically so that you can remember all the concepts that we have studied in this lecture. Thank you very much, guys.